Okay, so this is 3.6 part 2. I'm on page 17 with example number 4, and we're in the chain rule section. So if we look at this function, it says find the derivative of f of x where it equals x squared times the square root of 1 minus x squared. Once again, I can't simplify this, so unfortunately I'm going to have to use the product rule. So the product rule says that we take u times v prime plus v times u prime. Okay, so let's go ahead and write out what everything is. U is x squared, and the derivative of u equals 2x. V equals the square root of 1 minus x squared, or I can write this up as 1 minus x squared to the half power. And now for v prime, I'm going to have to use a chain rule because once again my inside function is kind of complicated. So I'm going to bring down the 1/2 because I'm going to do the outside first. So 1/2 times 1 minus x squared to the negative 1/2 power times, and now I'm going to take the derivative of the inside. So the derivative of 1 is 0, and the derivative of negative x squared is negative 2x. Okay, so I'm going to put the pieces together here. 1/2 times 2 is 1, so I get negative x times 1 minus x squared to the negative 1/2 power. All right, that's what the derivative is of v. Okay, so once again, I'm going to underline these just so we can see them a little bit clearer. Okay, so let's put the pieces together. uv prime plus vu prime. Okay, so u, once again, was x squared times v prime. V prime is negative x times 1 minus x squared to the negative 1/2 power plus v. V was 1 minus x squared to the 1/2 power times u prime, which is just 2x. Okay? All right, so if we put pieces together, I get negative x cubed times 1 minus x squared to the negative 1/2 power plus 2x times 1 minus x squared to the 1/2 power. If you want to make this look just a little bit better, you can get rid of the negative 1/2 powers. Remember, that's the square root. So I can write this up as negative x cubed over the square root of 1 minus x squared plus 2x times the square root of 1 minus x squared. I mean, that's about the best you can do. Okay, so let's go ahead and look at the next page, or the next example. I'm still on page 17. Find the derivative of y equals cosine cubed of 5t plus 1. All right, this function, we can rewrite this as cosine of 5t plus 1 to the 3rd power. So we can rewrite this like that. So if I do that, I'm going to have to use the chain rule actually 3 times because I'm going to have to take care of the outside function first, which is this. So let's go ahead and do this. So we get y equals 3 times cosine of 5t plus 1 to the 2nd power. Okay, so that's taking care of the outside first. Now I have to work my way in on the inside. So the inside function, I actually have cosine of a binomial. So I have to use the chain rule actually twice because I'm going to have to take care of the outside function cosine first. And if I do that, I get negative sine of 5t plus 1. And then now I have to finalize this by taking the derivative of the very, very inside, which is 5t plus 1. The derivative of that, the derivative of 5t is 5, and the derivative of 1 is 0. So I get times 5. So like I said, this becomes a little bit more hairy. All right, 5 times 3, 15. I have a negative from that sign. So I'm going to put the negative here. And I'm going to write this out as cosine, and I can bring the squared back in front of the 5t plus 1. And then I have sine of 5t plus 1. So this is about the best I can do with this. But once again, this one was a little bit weird because I had to use the chain rule 3 times on this. I had to do the outside function, which was the cube. Then I had to do the inside function, which I had cosine on the outside of a binomial, so I had to take care of the derivative of cosine. And then I had to take the derivative on the inside function of the 5t plus 1. Okay, so on the next page, which is page 18, we have a theorem of some general rules for derivatives with the chain rule. So if you have something complicated, like for instance, if I have, a binomial to the nth power, this becomes n times u to the n minus 1 times the derivative of u with respect to x. If I have sine with something complicated inside the parentheses, then I take the derivative of sine, which is cosine u, and then I take the derivative of the inside function, so that's du dx. If I take the derivative of tangent u, the derivative of tangent is secant squared u, and then I have to take the derivative of that inside function. So I take the derivative of u, which is du dx. Okay, if I'm taking the derivative of secant of something complicated, I take the derivative of secant, which is secant u tangent u, and then I take the derivative of whatever u is. So that's what du dx is. All right, and this one, if I take the derivative of e to the u, I take the derivative of e to the u times I take the derivative of u. Okay, we haven't seen this one yet, so we're going to see this one soon. And then if I take the derivative of cosine u, I have to take the derivative of cosine of something complicated, which is negative sine u, and then I have to take the derivative of that inside function, which is u, so that's du dx. If I take the derivative of cotangent u, the derivative of cotangent is negative cosecant u, and then I have to take the derivative of that u function. And finally, if I take the derivative of cosecant of something complicated, the derivative of cosecant is negative cosecant u cotangent u, and then I have to take the derivative of that inside function u, so that's why we got du dx. Okay? So now we're going to talk about the derivative of natural exponential functions and the chain rule, where u equals g of x. So the derivative of e to the x is just e to the x, okay? But what if you don't have an x that e is raised to? What if you have something weird, like a binomial? What do we do with that? So if we take the derivative of e to the u, where u is something complicated, then we take the derivative of e to the u times the derivative of u. Okay? So it's the chain rule again. Let's go ahead and look at example number 6 on page 18. Find the derivative of the original function is e to the 3x. So once again, this is more complicated than just e to the x. Okay? It's e to the 3x. So if we take and follow the rules, we do outside, which in this case is going to be e to the 3x, because remember the derivative of e to the x is just e to the x. And now I have to do the inside function. So the inside in this case is going to be this 3x. So the derivative of 3x is just 3. So the answer of this is going to be 3e to the 3x. Okay? All right, so chain rule again. All right, I'm going to look at B. We have y equals 2e to the negative x. So once again, this is not just x, it's e to the x. So if I follow the rules, I take pull the constant out, and I'm going to take the derivative of e to the negative x, which is just e to the negative x. And now I have to do this function, this inside function. So the derivative of the derivative of negative x is negative 1. So this becomes negative 2e to the negative x. And finally, we have c, which is y equals e to the 4 square root of x. Okay, so I'm going to just rewrite this really quick. So this is e of 4x to the 1/2 power. Okay, so it just looks a little bit better. So if I take the derivative of this, I take e to the 4x to the 1/2 power. Now I have to take the derivative of that. Okay, so when I take the derivative of 4x to the 1/2 power, I get 4 times 1/2 x to the negative 1/2 power. Okay, so the derivative is going to equal e to the 4x to the 1/2 times 2, because 4 times 1/2 is 2, x to the negative 1/2. So I'm going to write this up a little bit better. This is going to be 2 e raised to the 4 square root of x all over the square root of x. Okay? So that's the best I can do with that. And let's look at page 19. Okay, so we haven't dealt with exponential function when the base is a constant. So when the base is a constant, we're going to call that a. So we take the derivative with respect to x of a to the x. This actually equals the natural log of a times a to the x. Okay, so we've seen this rule before. So now what do we do when we have a constant where the power is complicated? So when the power is complicated, the answer to that is going to be the natural log of a times a raised to the u times the derivative of u. Okay? So again, never change the power of an exponential function when you take its derivative. Okay, so let's see how this all works. So we have example 7, find the derivative y equals 2 raised to 3x. So my base is 2, which is a value that's constant. So I'm going to apply that rule. Okay, so the rule says we take the natural log of 2 times 2 raised to whatever power it is. So that's 3x. Now I have to use the chain rule and take care of this 3x. So the derivative of 3x is 3. Okay, so this becomes 3 natural log 2 times 2 to the 3x. Okay, that's the best I can do. By the way, I cannot multiply the 3 and 2 together because they are not like terms. Okay, so let's look at b. We have a base 10, that's constant, raised to sine 3x. Okay, I know I have to use a chain rule on this because the sine 3x is complicated. So let's follow the rules. It says to take the natural log of the base, which is 10. And then what I have to do is take the base raised to the power. And then I have to take the derivative of the power. So sine of 3x, this is using the chain rule. I get cosine of 3x. And then I have to take the derivative of this inside function, which is 3. Okay, so I can rewrite this as 3 natural log 10 of cosine of 3x times 10 raised to the sine of 3x. And that's about the best I can do with this. All right, example number 8. Find the derivative of y equals 3 to the 2t over t. So unfortunately, I can't simplify this, or else I would. So I know that I have to use the quotient rule. And just a reminder again, it's low derivative of high minus high derivative of low over the square of what's below. Okay, so the low function is the denominator, which is t. The high function is the numerator, which is 3 raised to the 2t. The derivative of the high function. Okay, if I take the derivative of the high function, I'm going to use that rule we just saw. I'm going to take the base, which is 3, so it's going to be ln at 3 times the power itself, and then I have to take the derivative of this 2t, which is 2. Okay, so this becomes 2 ln of 3 times 3 to the 2t. Okay, now we have to take the derivative of the low function. The low function was just t, so we luck out because the derivative of t is 1. All right, so let's go ahead and put the pieces together. Low d high minus high d low over the square of what's below. Okay, so the low function, once again, was t. The derivative of the high function we found to be 2 times ln of 3 times 3 raised to the 2t minus the high function, which is 3 to the 2t, times the derivative of the low function, which is 1, all over the low function, which is t squared. Okay, all right, guys. So the only thing I do with this is multiply the t and the 2 together, so we get 2t ln of 3 times 3 raised to the 2t minus 3 to the 2t all over t squared. Okay, and that's it. So I'm going to just put brackets on this. Okay, so you can see that we use the chain rule a lot. The chain rule is definitely on the test, so please make sure you review it, make sure you understand it. These are videos, so you can go through them as many times as you want. And if you have any questions, please don't hesitate to ask.